What if gravity was wrong? Tonight, we're going to explore the most impossible planet astronomers have ever discovered. You've probably heard about Jupiter, our solar system's giant. But here's what most people don't realize. We found something that makes Jupiter look tiny, and it completely breaks our understanding of how planets form. This cosmic giant shouldn't exist according to everything we know about physics. By the end of this journey, you're going to question everything you thought you knew about planetary formation and the very laws that govern our universe. Before we dive in, if you enjoy these kinds of explorations, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a real difference for me. Get comfortable. Let's begin. You wake up every morning on a world that stretches 7,126 miles across. A sphere so vast that when you stand on any beach, any mountaintop, any street corner, the horizon curves away from you in every direction, creating the illusion of infinite flatness. If you could somehow walk in a straight line, never stopping, never resting, it would take you nearly 2 years of continuous walking to circle this planet we call home. Yet from where you sit right now, reading these words, the Earth feels solid, stable, comprehensible. But let me put this in perspective for you. A commercial airliner flying at 500 miles per hour would need more than 50 hours of continuous flight to circle our planet completely. That's longer than most people work in an entire week just to trace one line around the world beneath your feet. Think about your longest flight, maybe 8 hours across an ocean, and realize that wasn't even a sixth of our planet's circumference. And yet, when we look up at the night sky, when we start to measure our Earth against our neighboring worlds, something remarkable happens. Our intuition about size, about what it means to be large or small, begins to crumble. Mars, that rust-colored dot you can sometimes spot with your naked eye, stretches only 4,220 miles across, nearly half the size of Earth, appearing almost fragile in the cosmic vastness. If Earth were a basketball sitting in your hands, Mars would be a tennis ball. A world so much smaller than ours that you could fit nearly 3 Mars-sized planets inside Earth's volume. Yet Mars once had rivers, vast oceans, perhaps even life itself, flourishing on a world that now seems diminished and cold. Venus, our so-called sister planet, comes surprisingly close to Earth's dimensions at 7,521 miles in diameter. But that similarity in size masks a hellish reality where temperatures reach 864 degrees Fahrenheit, hot enough to melt lead, hot enough to destroy any spacecraft we've sent to its surface, within hours. The atmospheric pressure there would crush you instantly. Imagine the weight of an entire ocean pressing down on every square inch of your body. Mercury, the innermost planet, reveals itself as almost comically small at just 3,032 miles across. You could literally fit Mercury inside the continental United States with room to spare. If Earth were a basketball, Mercury would be a marble, a tiny sun-scorched marble racing around our star so quickly that a year there lasts only 88 Earth days. These rocky worlds, Mercury, Venus, Earth, Mars, they establish our first intuitive understanding of what it means to be a planet. They feel comprehensible, even if alien. You can imagine standing on their surfaces. You can picture their horizons. You can grasp their scales because they're not too far removed from our own experience. But then Jupiter appears. Jupiter stretches 88,146 miles across its equator, 11 times wider than Earth. When I tell you that 1,321 Earths could fit comfortably inside Jupiter's volume, your mind probably struggles with that number. Let me help you visualize this. If Earth were a grape, Jupiter would be a basketball. If Earth were a marble, Jupiter would be a beach ball. The mass of Jupiter, and this is where numbers start to lose meaning, equals 4.18, followed by 27 zeros pounds. That's 318 times more massive than our entire world. Jupiter contains more matter than all the other planets in our solar system combined with room to spare. It's less a planet than a failed star, a cosmic giant that came close to igniting nuclear fusion in its core, but fell just short of becoming a second sun in our sky. Think about this for a moment. Every time you look up at Jupiter through binoculars or a small telescope, you're seeing a world so massive that its gravitational pull shapes the orbits of comets throughout our solar system. Jupiter acts as a cosmic vacuum cleaner, protecting Earth from asteroid impacts by capturing or deflecting dangerous objects with its immense gravity. Without Jupiter's protection, life on Earth might never have had the stable, millions of years needed to evolve into the complex forms we see today. Saturn, with its 74,198-mile diameter, appears deceptively delicate because of those magnificent rings. But Saturn remains colossal. Those rings that make it so beautiful extend outward for 175,000 miles, more than 3/4 of the distance from Earth to our moon. If you could somehow drive a car along Saturn's rings at highway speed, the journey would take you more than 3 years of non-stop driving. Uranus presents us with 31,763 miles of diameter and the strange behavior of rotating on its side. As if some cosmic collision in the distant past knocked this world over, leaving it to roll along its orbit like a ball rather than spinning like a top. The seasons on Uranus last 21 Earth years each. Imagine a winter that spans your entire childhood. Neptune completes our family of gas giants at 30,175 miles across, orbiting so far from the Sun, 2 billion miles away, that sunlight takes more than 4 hours to reach it. If you could somehow travel at the speed of light, you could circle Earth's equator 7.5 times in just 1 second. Yet that same impossible speed would require 4 hours and 10 minutes to bridge the gap between our Sun and Neptune. Here's where perspective becomes crucial. If we could shrink our Sun down to the size of a basketball sitting on your table, Earth would become a grain of pepper about 26 yards away. At that scale, Jupiter would be a cherry about 135 yards from the basketball Sun. The entire solar system, out to Neptune's orbit, would fit within a single football stadium. But this familiar solar system, these worlds we've studied and sent spacecraft to visit, represents only the first step on a cosmic ladder that extends far beyond anything we could have imagined. Our intuition, shaped by walking on Earth's surface, by seeing our moon in the sky, by watching the planets move slowly among the stars, completely fails us when we venture beyond the boundary of our solar system. Everything we thought we knew about planetary limits, about what's possible in terms of size and mass and temperature, crumbles when we discover worlds orbiting other stars. In 1995, astronomers detected the first planet orbiting a sun-like star beyond our solar system. 51 Pegasi b, a world roughly Jupiter's mass but orbiting so close to its star that it completes 1 full year in just 4.2 Earth days. Imagine a world where summer, winter, spring, and fall cycle by in less than a single week, where temperatures soar above 1,132 degrees Fahrenheit, hot enough to melt copper. This discovery shattered our assumptions about how planetary systems form. We thought all gas giants would be cold, distant worlds like Jupiter and Saturn. We never imagined finding Jupiter-mass planets practically skimming the surfaces of their stars. Since that first discovery, we've confirmed more than 5,000 planets orbiting other stars. And what we've found challenges every assumption about planetary formation we held dear. Some of these distant worlds possess masses dozens of times greater than Jupiter, planets so massive they blur the line between planet and star. Worlds so large that Jupiter, our local giant, appears tiny by comparison. Modern telescopes can detect these cosmic giants at distances of hundreds or thousands of light-years from Earth. A single light-year represents 5.88 trillion miles. The distance light travels in one full year at 186,000 miles per second. Proxima Centauri, our nearest stellar neighbor, lies 424 light-years away. The light you see from that star tonight began its journey toward Earth when you were 4 years younger, and in that vast universe, separated by distances so extreme that light itself requires years or decades or centuries to bridge the gaps, we've discovered planets that shouldn't exist, worlds that our physics says are impossible, giants that make our Jupiter look like a marble next to a bowling ball. This journey we're beginning together will take us from the familiar confines of our solar system to planets so extreme they redefine what's possible in our universe. Worlds where iron rains from the sky, where temperatures exceed those found on some stars, where planets exist as barely coherent gas clouds larger than anything we thought physics would allow. You're about to discover that the universe doesn't care about our Earth-based intuition, our human-scale expectations, or our comfortable assumptions about how worlds should behave. Out there, in the darkness between the stars, nature has created giants that will make you question gravity itself. The first of these impossible worlds revealed itself in 1999 when astronomers detected something extraordinary happening 153 light-years from Earth. HD 299458b became the first planet we could actually watch as it passed directly in front of its host star. Think about that for a moment. For the first time in human history, we could see the shadow of another world orbiting another sun as it blocked a tiny fraction of starlight on its endless journey through space. This distant world possesses only 69% of Jupiter's mass, making it lighter than our familiar gas giant. But here's where our understanding begins to break down. Despite having less mass, HD 299458b stretches to 1.35 times Jupiter's radius. It's as if someone took Jupiter and inflated it like a cosmic balloon. The reason becomes clear when you consider its orbital distance. HD 299458b races around its star at a distance of only 4.3 million miles. To put this in perspective, our Sun is 93 million miles from Earth. This alien world orbits 22 times closer to its star than we orbit ours. The gravitational dance is so tight that HD 29458b completes an entire year in just 3.5 Earth days. At that distance, the stellar radiation heats the planet's atmosphere to a constant 2,066 degrees Fahrenheit. That's hot enough to melt aluminum, hot enough to turn solid rock into vapor. The intense heat causes the planet's atmosphere to expand outward like a hot air balloon, creating a world with a density of only 0.01 ounces per cubic inch. For comparison, water has a density of 0.58 ounces per cubic inch. This planet is literally lighter than cork. But HD 299458b was just the beginning. WASP-12b emerged from our surveys as something even more extreme. This world contains 1.41 times Jupiter's mass, but inflates to 1.79 times Jupiter's radius. The numbers alone don't capture the strangeness. Imagine a world so close to its star that it completes an orbit in just 26 hours. A planet where day and night cycle by faster than a single Earth day. The surface temperature of WASP-12b reaches 4,532 degrees Fahrenheit. That's hot enough to vaporize iron, hot enough to turn titanium into gas. The intense stellar radiation is literally boiling away the planet's atmosphere. Every second, WASP-12b loses approximately 417 billion pounds of its atmosphere to space. That's like losing the mass of Mount Everest every few hours. The planet is so hot, so inflated by the stellar heat, that it's being stretched into an egg shape by the gravitational forces. The side facing the star bulges outward, creating a world that looks more like a cosmic teardrop than a sphere. Material from the planet's atmosphere streams away into space, forming a comet-like tail millions of miles long. Then astronomers discovered WASP-17b. and the impossible became routine. This world defied everything we thought we knew about planetary physics. WASP-17b possesses only 48% of Jupiter's mass, making it lighter than Saturn. Yet its radius stretches to 1.93 times that of Jupiter. The resulting density drops to an almost incomprehensible 0.005 ounces per cubic inch. This is a planet with the density of styrofoam. To help you visualize this, if WASP-17b were somehow placed in a cosmic ocean, it would float like a cork. A world nearly twice Jupiter's size that weighs half as much as Jupiter itself. It's as if nature took a soap bubble and inflated it to planetary proportions. But WASP-17b holds another secret that challenges our understanding of how planetary systems form. This world orbits its star backward. While most planets orbit in the same direction their star rotates, WASP-17b travels in the opposite direction. It's like a runner going the wrong way around a track, suggesting that something violent happened during this world's formation. Perhaps gravitational encounters with other planets flung it into this retrograde orbit through a series of cosmic billiard ball collisions. HAT P1b presented astronomers with yet another puzzle. This world spans 1.36 times Jupiter's radius, but contains only 52% of Jupiter's mass. The density works out to roughly that of cork. If you could somehow compress HAT P1b down to the size of a baseball, it would weigh about as much as a ping-pong ball. The discovery of such low-density worlds forced astronomers to completely revise their models of planetary formation. According to our understanding of gravity and gas behavior, these inflated giants should collapse under their own weight. The fact that they maintain such expanded atmospheres suggests heating mechanisms we're only beginning to understand. In 2007, TRES-4b claimed the title of largest confirmed planet yet discovered. This world stretches to 1.84 times Jupiter's radius while containing 92% of Jupiter's mass. The volume works out to 84% larger than Jupiter. Imagine a world so expanded that you could fit nearly 2 Jupiters inside its boundaries. TRES-4 orbits just 4.3 million miles from its star, receiving radiation that heats its atmosphere to approximately 2,912 degrees Fahrenheit. For comparison, Mercury orbits our Sun at an average distance of 36 million miles. TRES-4b huddles 8 times closer to its star than Mercury does to ours. The catalog of inflated giants continued growing. WASP-79b revealed itself as another cork-density world, with 90% of Jupiter's mass inflated to 1.70 times Jupiter's radius. The density drops to 0.01 ounces per cubic inch, creating a planet that would float in water if such an ocean could exist. Then astronomers found XO3b, and suddenly we approached the boundary between planet and something else entirely. This world contains 11.79 times Jupiter's mass, while maintaining a radius only 1.22 times larger than Jupiter. Unlike the inflated giants, XO3b represents a massive world compressed by its own gravity into a relatively small space. At nearly 12 Jupiter masses, XO3b approaches the theoretical limit that separates planets from brown dwarfs. Beyond about 13 Jupiter masses, objects become massive enough to fuse deuterium in their cores. Brown dwarfs occupy this strange middle ground between planet and star, too massive to be planets, but too small to sustain the hydrogen fusion that powers true stars. WASP-33b orbits one of the hottest stars yet found to host a planet. The host star burns at a surface temperature of 13,406 degrees Fahrenheit, significantly hotter than our Sun's 9,932 degree surface. This creates a radiation environment so intense that WASP-33b experiences daytime temperatures exceeding 5,032 degrees Fahrenheit. That's hotter than some small stars, The CoRoT Space Telescope, operating from 2006 to 2012, detected dozens more of these inflated giants. CoRoT-1b, CoRoT-2b, and their companions expanded our catalog rapidly. Each new discovery revealed that what we initially thought were rare oddities were actually common throughout the galaxy. The diversity observed in just the first 50 exoplanets forced astronomers to confront an uncomfortable truth. Our solar system, with its orderly arrangement of small rocky worlds close to the Sun and gas giants farther out, represents just one possible architecture among countless variations. The universe had created planetary systems that bore no resemblance to our familiar arrangement. Every new discovery demanded revisions to our theories of planetary formation. How could planets form so close to their stars? How could they maintain such low densities? Why did so many orbit backward? The comfortable assumptions we'd built from studying our 8 familiar worlds crumbled in the face of this cosmic diversity. These first exoplanets were just the appetizer. As our detection methods improved, as our telescopes became more sensitive, we began finding worlds that made even these inflated giants seem ordinary. Planets so hot they rain vaporized metals. Worlds so close to their stars they complete orbits in mere hours. Giants so massive they blur the line between planet and failed star. The universe, it seemed, had saved its most extreme creations for us to discover. Each revelation prepared us for the next impossible world. Each impossibility became the new baseline for what planets could be. And waiting in the darkness, astronomers were about to find planets that would make everything we'd seen so far look conservative by comparison. The next class of worlds we discovered shattered every remaining assumption about planetary survival. These are the hot Jupiters, planets that huddle so close to their stars they experience temperatures that would vaporize mountains, melt steel, and turn rock into gas. Worlds where the very concept of weather becomes an exercise in exotic physics. WASP 189b orbits its star at a distance so close that its daytime temperatures reach 5,192 degrees Fahrenheit. To put this in perspective, that's hotter than many red dwarf stars. The surface of our Sun burns at 9,132 degrees, meaning this planet experiences more than half the temperature of stellar surfaces. Yet somehow, impossibly, it maintains its structure as a world, rather than simply evaporating into space. But here's what makes this even more extraordinary. The night side of WASP 189b, the hemisphere permanently facing away from its star, remains at 192 degrees Fahrenheit. Think about that. The cool side of this world is still hot enough to melt copper. This happens because atmospheric winds race around the planet at more than 11,000 miles per hour, carrying the intense heat from the day side to the night side in a constant, violent circulation. These aren't gentle breezes. These are supersonic hurricanes of vaporized metal and superheated gas, creating a global weather system unlike anything in our solar system. The entire planet exists in a state of perpetual atmospheric chaos, where the very air glows with heat. But WASP 189b isn't even the hottest world we've found. Kelt 9b currently holds the record as the most scorching planet known to exist. With temperatures reaching 8,212 degrees Fahrenheit, this world is literally hotter than some stars. The surface temperature exceeds that of many K-type stars, those orange-red suns that make up about 12% of all stars in our galaxy. Think about the implications here. We've discovered a planet that's hotter than a star. It challenges our very definition of what constitutes a planet versus what constitutes a stellar object. Kelt 9b contains 2.88 times Jupiter's mass, but inflates to 1.84 times Jupiter's radius due to the extreme heat. The planet is so hot that it's literally evaporating. Its atmosphere is being stripped away, molecule by molecule, creating a comet-like tail of planetary material streaming into space. The host star, Kelt 9, burns at 18,226 degrees Fahrenheit on its surface. That's nearly twice as hot as our Sun. This creates a radiation environment so intense that Kelt 9b loses between 40 billion and 150 billion tons of atmosphere every billion years. That's like losing between 18 and 68 Earth masses worth of material over cosmic time scales. The planet completes an orbit around this stellar furnace in just 1.5 Earth days. Imagine seasons that cycle by twice as fast as our weekends. A world where you could watch the sun rise and set 37 times in what we consider a single month. Mascara 1b presented astronomers with a detection challenge unlike any before. This planet orbits a star so blindingly bright that most telescopes couldn't observe it. The star was literally too bright for conventional planet hunting techniques. Only specialized instruments designed to handle extreme stellar brightness could detect the tiny dimming as this world passed in front of its star. WASP 103b pushes orbital proximity to almost unimaginable extremes. This world completes an entire orbit in just 22.2 hours, less than a single Earth day. The planet races around its star so quickly that it experiences gravitational forces intense enough to physically deform its shape. Instead of a sphere, WASP 103b has been stretched into an elongated, football-like shape by tidal forces. These tidal forces work the same way our moon creates ocean tides on Earth, but amplified millions of times. The difference in gravitational pull between the star-facing side of the planet and the far side is so extreme that it literally stretches the world into an oval. WASP 103b resembles a cosmic rugby ball, perpetually stretched toward its star. And this brings us to something even more extreme. TOI 849b represents what astronomers call a planetary core, what's left when stellar radiation strips away everything but the rocky heart of a former gas giant. This world contains 40.8 times Earth's mass, but maintains a radius of only 3.4 Earth radii. The density works out to 0.3 ounces per cubic inch, comparable to Earth despite being 40 times more massive. Imagine a world where the immense gravity has compressed rock and metal into densities we can barely comprehend. This isn't a gas giant anymore. It's the exposed skeleton of what was once probably a Neptune-sized world, baked and stripped by stellar radiation until only the ultra-dense core remains. WASP 121b exists at the very edge of planetary survival. This world orbits so close to its star that it approaches what astronomers call the Roche limit, the distance at which tidal forces become stronger than the planet's own gravity. If WASP 121b moved just slightly closer to its star, the gravitational differential would literally tear it apart. The planet is already showing signs of disintegration. Its upper atmosphere streams away into space, creating a tail of escaping material millions of miles long. Observations show heavy metals like iron and magnesium being stripped from the planet and flowing away in this cosmic wind. WASP 121b is slowly committing atmospheric suicide, bleeding itself into the void. But perhaps the most surreal of all these hellish worlds is WASP 76b, where the weather forecast includes liquid iron rain. The day side of WASP 76b reaches 4,352 degrees Fahrenheit, hot enough to vaporize iron, titanium, and other metals. These vaporized metals get caught up in the supersonic winds and carried to the night side of the planet. There, in the relatively cooler temperatures of 2,132 degrees Fahrenheit, the iron vapor condenses back into liquid droplets and falls as rain. Picture this: clouds made of vaporized metal, raindrops of molten iron falling through an atmosphere of superheated gas, lightning that arcs through metallic vapor. This is weather on a scale and at temperatures that render our Earth-based understanding of meteorology completely inadequate. HAT P7b demonstrated that we could actually observe these alien weather patterns from Earth. The Kepler Space Telescope detected brightness variations as different parts of the planet's atmosphere reflected varying amounts of starlight. We were seeing weather on a world 1,040 light-years away. Cloud formations of exotic materials drifting across the face of an alien world. Even planets orbiting cooler stars reach temperatures that defy comprehension. WASP 43b circles a red dwarf star, one of the coolest types of stars, yet still experiences temperatures of 2,732 degrees Fahrenheit due to its proximity. The temperature difference between its day and night sides exceeds 800 degrees Fahrenheit, creating thermal gradients that drive winds of incredible violence. HD 149026b revealed yet another surprise. This world possesses a rocky core containing approximately 70 Earth masses of heavy elements. That's like having 70 Earths worth of rock and metal compressed into the center of a single planet. The core represents 7% of the planet's total mass, far higher than any world in our solar system. These discoveries fundamentally changed our understanding of planetary survival. We learned that worlds can exist under conditions we previously thought would instantly destroy them. Planets can maintain coherent structures while experiencing temperatures that exceed stellar surfaces. Atmospheres can persist even while being constantly stripped away. Weather systems can function with liquid metal rain and supersonic metallic winds. The hot Jupiters taught us that the universe operates under rules far more extreme than our Earth-based experience suggested. These worlds exist in a state of constant catastrophe by our standards, yet they endure for millions or billions of years. They've expanded our definition of habitability, of planetary physics, of what's possible in the cosmic arena. But as extreme as these furnace worlds seemed, they were merely preparing us for discoveries that would stretch the boundaries of planetary physics even further. Worlds so massive they challenged the distinction between planet and star. Giants so inflated they defy our understanding of matter itself. But as extreme as these furnace worlds seemed, they were merely preparing us for discoveries that would stretch the boundaries of planetary physics even further. Worlds so massive they challenged the distinction between planet and star. The next frontier in our cosmic journey takes us to objects that exist in the twilight zone between planet and star. Superjupiters, worlds so massive that they begin to blur the fundamental definitions we use to categorize celestial objects. These are planets that weigh as much as small stars, yet somehow maintain their planetary identity in the face of gravitational forces that should crush them into stellar ignition. The HR 8799 system revealed itself as a laboratory for studying these massive worlds. Here, 129 light-years from Earth, astronomers discovered not one, but 4 super-Jupiter planets orbiting a single star. Each of these worlds contains between 5 and 7 Jupiter masses. To put this in perspective, that's like having 4 worlds in a single system, each weighing more than 1,500 Earths. These giants orbit at distances that dwarf even our outer solar system. The innermost planet, HR 8799e, circles its star at a distance of 870 million miles. That's nearly 10 times farther from its star than Earth is from our Sun. The outermost world, HR 8799b, travels in an orbit 4.2 billion miles from its star. For comparison, Neptune, our most distant major planet, orbits just 2.8 billion miles from our Sun. What makes the HR 8799 system so remarkable is that we can actually see these planets directly. Unlike most exoplanets, which reveal themselves only through indirect methods, the HR 8799 worlds shine brightly enough in infrared light that we can photograph them as distinct points of light separate from their star. We're looking at baby pictures of alien worlds, each one massive enough to be a failed star in its own right. HR 8799e, despite being one of the smaller planets in this system, still contains between 5 and 10 Jupiter masses. The uncertainty in its mass measurement illustrates one of the challenges astronomers face when dealing with such extreme objects. At these scales, the difference between a massive planet and a small brown dwarf becomes increasingly arbitrary. Beta Pictoris b pushes us right to the edge of that arbitrary boundary. This world contains approximately 13 Jupiter masses. That's significant because 13 Jupiter masses represents the theoretical dividing line between planets and brown dwarfs. Objects more massive than this threshold can ignite deuterium fusion in their cores, a process that separates them from true planets. Deuterium is heavy hydrogen. While normal hydrogen contains just one proton in its nucleus, deuterium adds a neutron to the mix. This extra neutron makes deuterium easier to fuse than regular hydrogen. Where true stars require the immense pressures and temperatures to fuse hydrogen into helium, objects with masses above 13 Jupiters can sustain deuterium fusion at much lower thresholds. Beta Pictoris, E sits right at this boundary, making it either the most massive planet possible or the least massive brown dwarf. Aurochs 44BB currently disputes the title of largest confirmed planet. This world contains 9 Jupiter masses, but inflates to 2.5 times Jupiter's radius. The volume works out to 15.6 times larger than Jupiter. Imagine a world so expanded that you could fit more than 15 Jupiters inside its boundaries. But ROX 42BB orbits at a distance that challenges our understanding of planetary formation. This world travels 9.7 billion miles from its star. That's more than 3 times farther than Neptune orbits from our Sun. At such distances, the traditional model of planet formation through gradual accretion becomes problematic. Most planetary formation theories suggest that worlds this massive should form through gravitational collapse. Rather than slowly building up from rocky cores that gradually accumulate gas, these super Jupiters probably condensed directly from the primordial disk of material surrounding their young stars. They're more like failed binary companions than traditional planets. Kappa Andromedae b presents us with another boundary case, weighing in at 12. 8. Jupiter masses. This world approaches dangerously close to the brown dwarf limit. The fact that it's only 30 million years old works in our favor for observation. Young planets still glow with the heat of their formation, making them bright enough to study directly, even at distances of hundreds of light years. The uncertainty in classifying these massive objects becomes apparent when we examine GQ Lupi b. Depending on which measurement technique astronomers use, this object could weigh anywhere from 10 to 36 Jupiter masses. If it's on the lighter end of that range, it's definitely a planet. If it's on the heavier end, it's clearly a brown dwarf. This uncertainty illustrates the challenge of studying objects at such extreme distances. ʻOumuamua 7b holds the distinction of being the first planet ever photographed directly. But even this achievement comes with complications. This world doesn't orbit a star at all. Instead, it circles a brown dwarf. With a mass estimated between 3 and 10 Jupiters, ʻOumuamua 7b blurs the line between planet and moon of a failed star. HD 106906b represents perhaps the most extreme orbital configuration yet discovered. This 11 Jupiter mass world orbits 40.3 billion miles from its star. To put this distance in perspective, that's more than 650 times farther than Earth orbits the Sun. At that distance, the star would appear as nothing more than a bright point of light, providing virtually no heat or gravitational influence. The orbital distance is so extreme that astronomers question whether HD 106906b actually formed in the system at all. Some theories suggest it might be a rogue planet that was gravitationally captured as it drifted through interstellar space. Alternatively, it might have formed closer to its star and been flung outward through gravitational interactions with other massive objects. HD 95086b shows us what these massive worlds look like when they're still relatively young. With a mass between 4 and 5 Jupiters, this world maintains a surface temperature of approximately 832 degrees Fahrenheit. That heat comes not from its distant star, but from the gravitational energy still being released as the planet slowly contracts under its own weight. Direct observation of HD 95086b required cutting-edge coronagraph technology. These specialized instruments block out the overwhelming light from the host star, revealing the much fainter glow of the planet itself. It's like trying to see a candle flame while standing next to a searchlight. 51. Eridani b represents one of the most thoroughly studied young superjupiters. With 2.6 Jupiter masses and an age of only 20 million years, this world provides astronomers with insights into how massive planets evolve over cosmic time. Spectroscopic analysis reveals water vapor and carbon monoxide in its atmosphere, giving us direct chemical signatures from an alien world. Perhaps most remarkable of all are PDS-70b and PDS-70c. These worlds are still forming. Astronomers have detected them within the protoplanetary disk of material surrounding their young star. PDS-70b contains between 4 and 17 Jupiter masses, but it remains surrounded by actively accreting material. We're watching planetary birth in real time. The disk of gas and dust around PDS-70b extends for millions of miles. Material from this disk continues to rain down onto the growing planet, adding mass and releasing gravitational energy that heats the world to thousands of degrees. This is planet formation as it happens, captured by our telescopes in unprecedented detail. These superjupiters force us to confront fundamental questions about the nature of planetary objects. Where exactly do we draw the line between a planet and a brown dwarf? Is it based purely on mass, on formation mechanism, on orbital characteristics? The universe seems to have created a continuous spectrum of objects that resist our human need for clear categories. What becomes clear is that the distinction between planet and star isn't as sharp as we once believed. There is a gray area populated by objects that share characteristics of both. Worlds massive enough to generate their own heat through gravitational contraction. Objects that form like stars but orbit like planets. Failed stars that never quite achieved stellar ignition. These discoveries prepare us for what lies ahead. If superjupiters challenge our definitions of planetary objects, the worlds we're about to encounter will shatter those definitions entirely. Planets so massive, so inflated, so impossible by our current understanding of physics that they force us to rewrite the rules of planetary science altogether. And then astronomers discovered worlds that shouldn't exist at all. HAT P67b represents the first planet that completely broke our understanding of how matter behaves under gravitational influence. This world stretches to 2.085 times Jupiter's radius, making it the widest planet with precise measurements ever confirmed. But here's where physics seems to fail. Despite this enormous size, HAT P67b contains only 34% of Jupiter's mass. Think about what this means. You have a world more than twice as wide as Jupiter, but weighing only 1/3 as much. The resulting density drops to an almost incomprehensible 0.003 ounces per cubic inch. That's approximately half the density of cotton candy. This is a planet with the consistency of carnival confection, somehow maintaining coherent structure across a volume 8 times larger than Jupiter. If you could somehow place HAT P67b in a cosmic bathtub filled with water, it would float like a cosmic sponge. Actually, it would float so high that only a small portion would sink below the surface. We're talking about a planet-sized soap bubble, held together by gravity so weak it shouldn't be able to maintain structural integrity. To put this density in perspective, consider that cork has a density of 0.01 ounces per cubic inch. HAT P67b is 3 times less dense than cork. If you could somehow compress this planet down to the size of a basketball, it would weigh about as much as a slice of bread. Yet this impossibly light world maintains a diameter of 184,000 miles. That's wider than the distance from Earth to our moon. But HAT P67b isn't even the least dense world we've found. WASP 193b pushes the boundaries of physical possibility even further. This world maintains a radius 1.464 times that of Jupiter while containing only 9% of Jupiter's mass. The density works out to 0.3 ounces per cubic inch. This planet is literally less substantial than styrofoam. If you could somehow hollow out a basketball and fill it with the same material as WASP 193b, it would weigh about as much as a ping-pong ball. Current theoretical models simply cannot explain how WASP 193b maintains its structure. According to our understanding of gravitational physics, a world this insubstantial should collapse under its own weight or be torn apart by the gravitational forces of its host star. The planet experiences temperatures of over 200 degrees Fahrenheit, which should cause even more atmospheric expansion. Yet somehow, impossibly, it endures. The heating mechanisms that create these cotton candy worlds remain one of astronomy's greatest puzzles. Normal stellar radiation, even at the closest orbital distances, cannot account for the extreme degree of atmospheric inflation we observe. Some exotic process must be pumping additional energy into these planetary atmospheres. Perhaps tidal heating from gravitational interactions. Perhaps magnetic field interactions with charged stellar winds. Perhaps mechanisms we haven't even imagined yet. Kepler 51d joins this category of cotton candy planets with a density of 0.003 ounces per cubic inch. But Kepler 51d presents an additional mystery. This world exists in a system with multiple low-density planets. Kepler 51b and Kepler 51c also exhibit densities far below what theoretical models predict. Finding multiple superinflated worlds in a single system suggests that whatever process creates these impossible densities operates on a system-wide scale. The existence of planets with densities below 0.003 ounces per cubic inch contradicts every established model of planetary evolution. Theoretical calculations suggest that planets this inflated should collapse under their own gravity within a few million years. The gravitational force trying to compress the planet should overwhelm any heating mechanism trying to inflate it. Yet these worlds have somehow maintained their expanded structure for hundreds of millions or billions of years. Computer simulations of planetary formation simply cannot reproduce these ultra-low densities. When astronomers input realistic parameters for stellar heating, atmospheric composition, and gravitational compression, the models consistently produce planets with densities at least 10 times higher than what we observe. It's as if these planets are following different physical laws than the ones we understand. And then there's HD 10546b, a world that disputes every assumption about planetary size limits. This object presents us with measurement uncertainties that reflect the extreme nature of what we're observing. Conservative estimates place HD 10546b at 3.4 times Jupiter's radius, but other measurements suggest it could be as large as 6.9 times Jupiter's radius. If the larger estimate proves correct, HD 10546b would possess a volume 330 times greater than Jupiter. That's like comparing a marble to a bowling ball. The measurement difficulties arise from the presence of a circumplanetary disk, a structure of dust and gas orbiting the planet itself, similar to, but far larger than Saturn's rings. This disk extends for hundreds of thousands of miles around the planet, obscuring direct observations and making precise size measurements extremely challenging. The disk contains enough material to form several Earth-sized moons, all swirling around a planet that may itself be impossible. The mass estimates for HD 10546b vary even more dramatically than its size measurements. Depending on which theoretical model astronomers apply, this world could weigh anywhere from 1.65 to 25 Jupiter masses. This enormous range in mass estimates reveals how little we understand about objects at these extreme scales. If HD 10546b weighs only 65 Jupiter masses, but spans 6.9 Jupiter radii, its density would be lower than any planet yet discovered. If HD 10546b truly possesses 6.9 Jupiter radii, we're looking at an object that challenges the very definition of a planet. At what point does an inflated gas giant become something else entirely? When does a planet become a diffuse cloud of matter held together by gravity alone? The planet's circumplanetary disk suggests it's still actively accreting material, growing larger even as we observe it. We may be witnessing the formation of an object unlike anything in our current classification system. The age of the HD 10546 system adds another layer of impossibility. At less than 10 million years old, this system is incredibly young by cosmic standards. Traditional planetary formation theory suggests that giant planets require tens of millions of years to accumulate the gas needed to become supermassive. Yet HD 10546b appears to have achieved extraordinary size in a fraction of that time. Either our models of planetary formation are fundamentally wrong, or this world formed through some rapid process we don't yet understand. The classification system breaks down entirely when we encounter objects like Dennis P. J082313.1 Wanda 491201b. This world contains 28.5 Jupiter masses, placing it firmly in brown dwarf territory according to the International Astronomical Union. Objects above 13 Jupiter masses can fuse deuterium in their cores, theoretically making them brown dwarfs rather than planets. But Dennis P. J. is joint to 3.1 b orbits a normal star, like any other planet. It formed in a planetary system, behaves like a planetary object, and shares orbital characteristics with other planets. The arbitrary 13 Jupiter mass limit suddenly seems inadequate when confronted with the reality of how these objects actually exist in nature. The IAU defines planets as objects with masses below 13 Jupiter masses. Objects between 13 and 75 Jupiter masses qualify as brown dwarfs, capable of intermittent deuterium fusion. Above 75 Jupiter masses, objects become true stars, sustaining continuous hydrogen fusion. But these neat categories fail to capture the messy reality of cosmic object formation. Consider the implications. If Dennis P. J082303.1491201b is technically a brown dwarf, then our solar system contains no analog to one of the most common types of objects in planetary systems. We're trying to understand cosmic diversity using a sample size of 8 worlds, none of which represents the extreme conditions found throughout the galaxy. WD 1856-534b presents perhaps the most impossible survival story in our catalog. This world orbits a white dwarf, the collapsed remnant of a star that once burned like our Sun. White dwarfs possess masses similar to our Sun, but compressed into volumes comparable to Earth. The density reaches millions of times that of water. Its matter crushed to the limits of what atomic structure can withstand. But here's the impossible part. WD 1856-534b somehow survived its star's red giant phase. When stars like our Sun exhaust their nuclear fuel, they expand into red giants hundreds of times their original size. This expansion should have engulfed and destroyed any nearby planets. The star would have grown to encompass the orbit of Mars, vaporizing everything in its path. Yet WD 1856-534b endures, orbiting the stellar remnant every 34 hours. The planet's survival requires explanations that stretch our understanding of stellar evolution. Perhaps the planet migrated inward after the red giant phase ended, spiraling through the expanding stellar atmosphere without being completely destroyed. Perhaps it formed from debris after the original planets were vaporized. Perhaps it's actually the exposed core of a much larger gas giant that was partially consumed by the dying star. Each explanation requires mechanisms we don't fully understand. The white dwarf itself presents extreme conditions. With a surface temperature of over 31,000 degrees Fahrenheit, it radiates intense ultraviolet radiation that should strip away any planetary atmosphere within thousands of years. Yet the planet maintains a stable orbit, apparently unaffected by the hostile radiation environment. We're looking at a world that has survived multiple apocalypses. TOI 2109b pushes orbital extremes to their absolute limits. This world completes an orbit around its star in just 16.1 hours. That's faster than most workdays. The orbital proximity results in the planet receiving 3,000 times more radiation than Earth receives from our Sun. The planet orbits at a distance of only 1.49 million miles from its star. For comparison, our Moon orbits Earth at a distance of 239,000 miles. At that distance and radiation level, TOI 2109b should be torn apart by tidal forces. The difference in gravitational pull between the star-facing hemisphere and the far side should exceed the planet's ability to hold itself together. The Roche limit, the distance at which tidal forces overcome gravitational binding, should have been crossed long ago. Yet the world persists, racing around its star in defiance of every calculation. The surface temperature reaches over 4,100 degrees Fahrenheit. That's hot enough to vaporize tungsten. The planet experiences day-night temperature variations of over 2,700 degrees Fahrenheit as it rotates. Atmospheric winds driven by these temperature differences should reach supersonic speeds, creating weather patterns that could tear apart the planet's structure. WASP-18b offers us a glimpse of planetary death in real time. This world is spiraling inward toward its star through tidal interactions. The planet's gravity raises bulges on the star's surface, while the star's gravity distorts the planet. These mutual distortions create friction that robs the planet of orbital energy. Calculations indicate that WASP-18b will be engulfed by its host star in approximately 650,000 years. That might seem like a long time by human standards, but it's an eye blink in cosmic terms. We're witnessing the final chapter of a planet's existence, watching as it slowly surrenders to the inexorable pull of gravity. Every orbit carries it slightly closer to destruction. Every day brings it nearer to the stellar surface that will ultimately consume it. K225b orbits a red dwarf star only 200 million years old. While this might seem ancient by human standards, it's remarkably young in cosmic terms. Our Sun is 4.6 billion years old. The stellar youth results in intense magnetic activity, bombarding the planet with energetic radiation and charged particles. Young red dwarfs produce stellar flares, thousands of times more powerful than anything our Sun generates. The planet endures a constant barrage of stellar fury that should strip away its atmosphere within millions of years. High-energy particles and X-rays blast the upper atmosphere, breaking apart molecules and allowing gases to escape to space. Yet K225b maintains a substantial atmosphere, suggesting either rapid atmospheric replacement or protective mechanisms we don't understand. These impossible planets force us to confront the limitations of our Earth-based intuition. We've discovered worlds that float like cosmic soap bubbles, planets that survive stellar explosions, objects that orbit so quickly they complete years in less than a day. Each discovery reveals that the universe operates under rules far more extreme and diverse than our comfortable solar system suggested. The cotton candy planets challenge our understanding of matter itself. How can gravitational objects maintain such low densities? The survivors of stellar death question our models of planetary system evolution. How do worlds endure conditions that should destroy them? The ultra-short period worlds push orbital mechanics to breaking points we thought impossible. How do planets maintain coherent structure under such extreme tidal forces? Every answer we find raises new questions. Every solution reveals new mysteries. The universe seems determined to create objects that defy our most fundamental assumptions about how matter behaves under extreme conditions. These discoveries prepare us for the ultimate revelation. Hidden in our catalogs of impossible planets lies a world so extreme, so defiant of physical laws, that it represents the absolute limit of what we thought possible in planetary formation. A planet that shouldn't exist according to everything we know about gravity, matter, and the fundamental forces that shape our universe. But how do we actually find these impossible worlds? How do astronomers working with telescopes separated by vast distances from their targets manage to detect and measure objects that challenge the very foundations of planetary physics? The methods we use to discover exoplanets are almost as remarkable as the worlds themselves. The most successful technique for finding planets relies on a simple principle. When a planet passes directly in front of its host star, as seen from Earth, it blocks a tiny fraction of the star's light. This transit method has revolutionized our understanding of planetary systems, allowing us to detect thousands of worlds that would otherwise remain invisible. The amount of light blocked during a transit reveals the planet's size directly. The relationship follows basic geometry. If a planet has twice Jupiter's radius, it blocks 4 times more starlight during its passage. A planet with 3 times Jupiter's radius blocks 9 times more light. This mathematical relationship allows astronomers to calculate precise planetary radii from the depth of the transit signal. But detecting these tiny changes in starlight requires extraordinary precision. When Jupiter transits the Sun as seen from a distant star, it blocks only 1% of the Sun's light. Earth's transit would block merely 0.08% of solar brightness. We're measuring changes in starlight, equivalent to detecting the shadow of a fruit fly crossing a searchlight beam from several miles away. The Kepler Space Telescope, operating from 2009 to 2018, perfected this technique with unprecedented accuracy. Kepler could detect brightness variations smaller than 0.01%. To put this sensitivity in perspective, Kepler could spot the dimming caused by a single candle being extinguished in the blazing lights of Times Square. This extraordinary precision allowed Kepler to discover thousands of exoplanets, including many of the impossible worlds we've discussed. Kepler monitored more than 200,000 stars continuously, watching for the telltale dimming that signals a planetary transit. The spacecraft had to maintain pointing stability accurate to within 0.01 degrees. That's like aiming a laser pointer at a penny from 100 miles away and keeping it steady for years. Any wobble, any vibration, any drift would contaminate the delicate measurements needed to detect Earth-sized worlds. The radial velocity method approaches planet detection from an entirely different angle. Rather than watching planets block starlight, this technique detects the gravitational wobble that planets induce in their host stars. Every planet-star system actually orbits around their common center of mass. For massive planets orbiting close to their stars, this creates measurable stellar motion. Stars don't remain perfectly stationary as planets orbit them. They wobble back and forth in response to gravitational tugs from their planetary companions. When the star moves toward Earth during its wobble, its light shifts slightly toward the blue end of the spectrum. When it moves away from us, the light shifts toward red. This Doppler effect creates spectral signatures that reveal both the planet's mass and orbital period. The precision required for radial velocity measurements pushes the boundaries of observational astronomy. Detecting Jupiter from another star system requires measuring stellar velocities of about 40 feet per second. That's slower than most people jog. Detecting Earth requires precision of just 3 feet per second. The most advanced spectrographs can now measure stellar motions as small as 3 feet per second, opening the possibility of finding truly Earth-like worlds. The HARP spectrograph, mounted on the 3.6-meter telescope at La Silla Observatory in Chile, represents the pinnacle of radial velocity precision. HARPs can detect stellar motion changes as small as 3 feet per second. To achieve this precision, the instrument must be isolated from vibrations, maintained at constant temperature, and calibrated using precise reference sources. The entire system resembles a laboratory experiment more than a traditional telescope. But for the most massive and unusual planets, astronomers can sometimes photograph them directly. Direct imaging requires blocking out the overwhelming light from the host star to reveal the much fainter glow of the planet itself. The brightness difference between stars and planets ranges from 1 billion to 10 billion times. It's like trying to photograph a firefly hovering next to a searchlight. Advanced coronagraphs use precisely shaped masks and adaptive optics to suppress starlight while preserving the planet's faint signal. The Hubble Space Telescope and James Webb Space Telescope employ these techniques to photograph young, massive planets that still glow with the heat of their formation. These direct images provide our only visual confirmation of worlds orbiting other stars. Astrometry offers another approach to planet detection by measuring the precise positions of stars over time. As planets orbit their stars, the gravitational interaction causes the star to trace a small ellipse in space. For nearby star systems, these positional changes can be measured with sufficient precision to detect massive planets. The European Space Agency's Gaia mission has perfected astrometric planet detection. Gaia measures stellar positions with accuracy of 10 microarcseconds. That's equivalent to measuring the width of a human hair from 600 miles away. This extraordinary precision allows Gaia to detect the gravitational influence of planets by observing how they affect their host stars' motion through space. Our own solar system center of mass illustrates this principle. The gravitational influence of all the planets, especially Jupiter, shifts the solar system's center of mass to a point just outside the Sun's surface. From a distant star system, alien astronomers could detect this wobble and deduce the presence of Jupiter without ever seeing it directly. Gravitational microlensing exploits Einstein's prediction that massive objects bend spacetime. When a planet and its star pass directly between Earth and a background star, the gravitational field acts as a lens, temporarily magnifying the background star's light. These lensing events last from hours to months and can reveal planets that would be undetectable by other methods. Microlensing events are unique and non-repeatable. Unlike transit or radial velocity signals that occur regularly as planets orbit their stars, each gravitational lensing event happens only once. This makes microlensing particularly valuable for detecting rogue planets, worlds that have been ejected from their birth systems and now drift freely through interstellar space. Einstein's general relativity predicted gravitational lensing decades before we had the technology to observe it. Now we use this exotic effect routinely to discover planets around stars thousands of light years away. We're employing the curvature of space-time itself as a cosmic magnifying glass. Pulsar timing represents perhaps the most precise planet detection method ever developed. Pulsars are rapidly rotating neutron stars that emit beams of radiation with clockwork regularity. These stellar lighthouses maintain timing accuracy that rivals atomic clocks. Any gravitational perturbation from an orbiting planet shows up as tiny variations in the pulsar's rhythm. PSR B11257+, Watch 12, became the first confirmed planetary system discovered around any star other than our Sun. Astronomers detected timing variations in this pulsar's signals that could only be explained by the presence of multiple planets. The precision required for pulsar timing exceeds anything else in astronomy. We're measuring changes in arrival times of just millionths of a second across distances of hundreds of light years. Secondary eclipse photometry allows astronomers to measure the heat emitted by exoplanets directly. When a planet passes behind its star during its orbit, the combined light from star and planet drops slightly as the planet's thermal emission is blocked. The difference between primary transit, planet in front of star, and secondary eclipse, planet behind star, reveals the planet's temperature and atmospheric properties. Transit spectroscopy opens a window into alien atmospheres. As a planet transits its star, some starlight passes through the planet's atmosphere before reaching Earth. Different atmospheric molecules absorb specific wavelengths of light, creating spectral fingerprints that reveal atmospheric composition. We can detect water vapor, carbon dioxide, methane, and other compounds in atmospheres light years away. The James Webb Space Telescope has revolutionized atmospheric studies of exoplanets. Its unprecedented infrared sensitivity allows detailed spectroscopic analysis of dozens of alien atmospheres. Webb has detected water vapor, carbon dioxide, clouds, and even weather patterns on worlds orbiting other stars. We're studying the meteorology of planets we'll never visit. Polarimetry measures how planet-reflected starlight becomes polarized. Different surface materials and atmospheric conditions affect light polarization in characteristic ways. This technique can distinguish between rocky surfaces, thick atmospheres, and even the presence of clouds or hazes. Polarimetric observations provide information about planetary properties that would be impossible to obtain through other methods. Phase curve observations track how a planet's brightness changes as it orbits its star. Like our moon showing phases, exoplanets reflect varying amounts of starlight depending on their orbital position. These brightness variations reveal information about atmospheric circulation, temperature distribution, and even the presence of weather systems. Some of the most remarkable discoveries combine multiple detection methods. The impossible cotton candy planets were first discovered through transit photometry, which revealed their enormous sizes. Follow-up radial velocity observations measured their surprisingly low masses. Atmospheric spectroscopy confirmed their inflated structures. Only by combining these diverse techniques could astronomers confirm that such worlds actually exist. The precision required for these measurements pushes technology to its limits. Detecting Earth-sized planets around Sun-like stars requires measuring brightness changes of 0.08%, recording stellar wobbles of 3 feet per second, tracking positional changes of microarc seconds. Each technique demands instruments operating at the very edge of what's physically possible. Modern exoplanet science resembles forensic investigation more than traditional astronomy. We gather clues from multiple sources: photometric evidence of planetary transits, spectroscopic fingerprints of atmospheric composition, astrometric measurements of stellar motion, gravitational signatures in pulsar timing. Each piece of evidence contributes to our understanding of worlds we can never visit directly. These technological marvels have revealed a universe far stranger than anyone imagined. Cotton candy planets that shouldn't maintain their structure. Worlds orbiting stellar corpses they should never have survived. Giants so massive they blur the line between planet and star. Each impossible discovery was made possible by pushing our instruments beyond what seemed achievable. The methods we've developed to find impossible planets continue to evolve. Future telescopes will detect even smaller worlds around more distant stars. Space-based interferometry will photograph planetary surfaces directly. Advanced spectroscopy will search for biological signatures in alien atmospheres. Each technological advance reveals new categories of impossible worlds. These detection methods have fundamentally changed how we understand planetary systems. Before we could observe exoplanets, our theories were based entirely on our solar system. 8 familiar worlds orbiting in predictable patterns. Now we know that our orderly arrangement represents just one possibility among countless exotic architectures scattered throughout the galaxy. But this raises a profound question. What are the ultimate limits? How large can a planet become before it stops being a planet at all? As we venture into the realm of extreme scales, we discover that the universe operates according to rules that dwarf even the most impossible worlds we've discussed. Jupiter represents something close to the maximum radius that gas giant planets can achieve under normal formation conditions. This might seem surprising given the inflated cotton candy worlds we've encountered, but Jupiter's size reflects a fundamental balance between gravitational compression and internal pressure. As planets accumulate more mass, their stronger gravity actually makes them smaller, not larger. Planets containing more than one. 6. Jupiter masses begin to compress gravitationally, reducing their radii despite their increased mass. It's counterintuitive. You add more material to a planet, but the planet shrinks. This happens because the additional mass creates stronger gravitational forces that compress the existing material more tightly. To understand why this occurs, consider the conditions inside massive planets. At the core of a planet containing 3 Jupiter masses, pressures reach 87 million pounds per square inch. That's 600 trillion times the atmospheric pressure at Earth's surface. Under such extreme conditions, matter behaves in ways that have no analog in our everyday experience. These crushing pressures transform hydrogen into an exotic state called metallic hydrogen. Under normal conditions, hydrogen exists as individual molecules or atoms. But when compressed to millions of pounds per square inch, the electrons separate from their protons and move freely through the material. Metallic hydrogen conducts electricity like liquid metal, creating powerful magnetic fields and entirely new physical properties. Scientists have created metallic hydrogen in Earth-based laboratories, but only under pressures exceeding 7.2 million pounds per square inch and at temperatures near absolute zero. The material remains stable for only microseconds before reverting to normal hydrogen. Yet inside massive planets, metallic hydrogen forms the dominant component, existing in quantities millions of times greater than our entire planet. Planets containing 10 Jupiter masses possess radii similar to or even smaller than Jupiter itself. All that additional mass gets compressed into a similar volume. The gravitational force trying to compress the planet overwhelms any heating mechanism trying to expand it. These worlds become incredibly dense balls of exotic matter, held together by gravitational forces that would instantly crush anything we recognize as normal matter. The theoretical upper limit for planetary mass approaches 13 Jupiter masses. Beyond this threshold, objects become massive enough to initiate deuterium fusion in their cores. Once nuclear fusion begins, even intermittently, we're no longer dealing with a planet. We've crossed into the realm of brown dwarfs, failed stars that never quite achieved full stellar ignition. Brown dwarfs can accumulate masses up to 75-80 Jupiter masses before they become massive enough to sustain hydrogen fusion. At that point, they transform into true stars. The smallest known star, EBLM J05557AB, contains only 85 Jupiter masses and maintains a radius similar to Saturn. It's a star smaller than some planets, yet burning nuclear fuel in its core, like our Sun. To put planetary masses in cosmic perspective, consider that Proxima Centauri, our nearest stellar neighbor, weighs 254 Jupiter masses. Even our relatively modest Sun contains 1,048 Jupiter masses. If Jupiter were a marble, our Sun would be a basketball. The mass difference between planets and stars spans orders of magnitude. But stars themselves exist across an enormous range of masses. The most massive star yet discovered, our 136A1, contains approximately 315 solar masses. That's equivalent to 331,000 Jupiter masses. If we could somehow shrink our 136A1 to the size of a basketball, Jupiter would be smaller than a grain of sand, completely invisible without powerful magnification. Our 136A1 burns so brilliantly that it loses mass through stellar winds powerful enough to strip material from nearby stars. This cosmic giant shines with the brightness of 8.7 million suns. If our 136A1 replaced our Sun, Earth would be vaporized instantly. The planet would simply cease to exist. Yet even the most massive stars pale in comparison to stellar remnants. When stars exhaust their nuclear fuel and collapse, they can form black holes with masses ranging from 3 to 20 solar masses. That's equivalent to 3,150 to 21,000 Jupiter masses, compressed into regions smaller than major cities. The gravitational fields become so intense that space and time themselves become severely distorted. At the center of our galaxy lurks Sagittarius A, a supermassive black hole containing 4.3 million solar masses. If this monster were somehow given a physical radius, it would extend 273 million miles from its center. That's larger than the orbit of Mars. Yet all this mass occupies a region where the known laws of physics break down entirely. Sagittarius A seems almost modest compared to the universe's largest black holes. Tune 618, located 10.4 billion light-years from Earth, contains 66 billion solar masses. The event horizon of this cosmic leviathan extends for 808 billion miles. That's more than 800 billion miles of pure gravitational annihilation. For comparison, Pluto orbits our Sun at a distance of 3.67 billion miles. If TON 618 occupied the center of our solar system, its event horizon would extend far beyond Pluto's orbit. The entire solar system, out to the heliopause, would be trapped within this black hole's gravitational prison. Light itself cannot escape from within these boundaries. Matter, energy, information, all become trapped forever. These extreme objects help us understand planetary limits through cosmic perspective. Our galaxy contains between 100 and 400 billion stars distributed across a disk 100,000 light-years in diameter. Each point of light represents a potential solar system, possibly containing planets that make our most extreme discoveries seem ordinary. The Andromeda galaxy, our nearest major galactic neighbor, stretches across 220,000 light-years and contains over 1 trillion stars. Andromeda approaches us at 250,000 miles per hour, but the collision won't occur for another 5 billion years. When it does, the gravitational interactions will reshape both galaxies, flinging star systems into intergalactic space and creating new environments for planet formation. Our local group contains more than 80 galaxies within a region, approximately 10 million light-years across. The Virgo cluster, our nearest major galaxy cluster, houses more than 1,300 galaxies in a volume spanning 15 million light-years. Each galaxy contains billions or trillions of stars, each star potentially hosting planetary systems. The largest structures in the universe dwarf even galaxy clusters. The Sloan Great Wall extends for 1.37 billion light-years, forming one of the largest coherent structures known to exist. This cosmic web of galaxies and dark matter represents organization on scales that challenge our understanding of how the universe evolved from initial conditions. The observable universe itself spans 93 billion light-years in diameter. This contains approximately 2 trillion galaxies, each hosting billions of stars. If we conservatively estimate that each star hosts an average of 1.6 planets, the observable universe contains roughly 10 to 24 planets. That's a trillion worlds. To put this number in perspective, imagine counting every grain of sand on every beach on Earth. Then multiply that number by 1,000,000. You still haven't reached the estimated number of planets in the observable universe. Statistical analysis suggests that planets larger than any we've discovered almost certainly exist in unexplored systems. Our current observational limitations restrict planet detection to within a few thousand light-years of Earth. We're sampling an incredibly tiny fraction of our galaxy, let alone the observable universe. Future space-based telescopes will extend our reach, potentially detecting planets in nearby galaxies. Each new survey revealing planetary populations we can barely imagine. The James Webb Space Telescope represents just the beginning. Proposed missions like the Habitable Exoplanet Observatory will photograph Earth-like worlds directly. Advanced interferometry will resolve planetary surfaces. Space-based arrays will search for biosignatures in alien atmospheres. Each technological advance opens new windows into cosmic diversity. Consider what this means for planetary extremes. If cotton candy planets with impossible densities exist in our tiny local sample, what exotic worlds await discovery in the vast regions we haven't yet explored? If we've found planets orbiting white dwarf stellar corpses in our immediate neighborhood, what survivors exist around neutron stars or in the accretion disks of black holes? The universe operates on scales that make our most extreme planetary discoveries seem conservative. We've found worlds that challenge physics, but we've barely begun to sample the cosmic inventory. Somewhere in the darkness between distant stars, nature has almost certainly created planets that exceed every limit we've discussed. These extreme scales prepare us for the ultimate revelation. Among all the impossible worlds we've cataloged, one stands out as the most defiant of physical laws. A planet so large, so unlikely, so contrary to everything we understand about planetary formation that it represents the absolute boundary of what's possible in our universe. HD 10546b remains the most controversial and extreme planetary candidate ever discovered. This world challenges not just our understanding of planetary physics, but the very foundations of how matter behaves under gravitational influence. Conservative estimates place HD 10546b at 3.4 times Jupiter's radius. But some measurements suggest something far more extraordinary, a world spanning 6.9 times Jupiter's radius. If the larger estimate proves correct, HD 10546b would possess a volume 330 times greater than Jupiter. Think about that for a moment. You could fit 330 Jupiters inside the boundaries of this single world. If Jupiter were a marble, HD 10546b would be a beach ball. If Jupiter were a basketball, HD 10546b would be the size of a small building. The mass estimates for this impossible world vary even more dramatically than its size measurements. Depending on which theoretical model astronomers apply, HD 10546b could weigh anywhere from 1.65 to 25 Jupiter masses. This enormous uncertainty reflects how little we understand about objects operating at these extreme scales. If HD 10546b truly spans 6.9 Jupiter radii while weighing only a few Jupiter masses, its density would be lower than anything we've discovered. HD 10546b orbits 4.9 billion miles from its host star. That's farther than Neptune orbits from our Sun. At such distances, traditional planetary formation theory breaks down entirely. The star HD 100546 represents a young, massive system less than 10 million years old. That's incredibly young by cosmic standards. Our solar system is 460 times older. The extreme youth of this system suggests that HD 100546b is still actively forming. We may be witnessing planetary birth on a scale never before observed. Telescopic observations reveal a circumplanetary disk surrounding HD 10546b, a rotating structure of dust and gas extending for millions of miles around the planet itself. This disk contains enough material to form 1.44 Earth's worth of mass within a radius of 41 million miles. The existence of this circumplanetary disk indicates that HD 10546b continues to accrete material from its surroundings. The planet is literally growing as we observe it. Material from the disk rains down onto the planet's surface, releasing gravitational energy that heats the world to thousands of degrees. We're watching the construction of a cosmic giant in real time. Traditional models of planetary formation cannot explain how HD 10546b achieved such enormous size so quickly. The standard core accretion model requires millions of years to build gas giant planets through gradual accumulation. First, rocky planetesimals collide and stick together to form solid cores. Then, once these cores reach sufficient mass, they begin capturing gas from the surrounding disk. This process should take 50 to 100 million years to create Jupiter-sized worlds. But HD 10546b appears to have reached its current size in less than 10 million years. The host star itself is younger than the time traditional theory requires for giant planet formation. Either our models are fundamentally wrong, or this world formed through an entirely different process. HD 10546b likely formed through gravitational instability. Rather than slowly building up from solid cores, the planet probably condensed directly from the protoplanetary disk through rapid gravitational collapse. This process can create massive planets in thousands of years rather than millions. Sections of the disk become gravitationally unstable and collapse into planetary mass objects almost instantaneously. However, gravitational instability requires very specific conditions of disk mass, temperature, and stellar radiation that rarely align. The disk must be massive enough to become gravitationally unstable, but not so massive that it forms multiple competing objects. The temperature must be low enough to allow gas to condense, but warm enough to prevent the entire disk from fragmenting. These conditions occur in perhaps 1% of young stellar systems. The effective temperature of HD 10546b reaches 1218 degrees Fahrenheit. This temperature is consistent with a young world still contracting under its own gravity. As the planet slowly shrinks, gravitational potential energy converts to heat, causing the world to glow like a cosmic ember. This process, called Kelvin-Helmholtz contraction, can maintain planetary luminosity for millions of years. The luminosity of HD 10546b equals 0.023% of our Sun's total output. That might seem small, but it's extraordinarily bright for a planetary object. For comparison, Jupiter emits only 0.001% of solar luminosity. HD 10546b shines 23,000 times brighter than Jupiter. This intense luminosity suggests the planet still radiates primordial heat from its violent formation. Planets formed through traditional core accretion should be much cooler by now. After 10 million years, most of the formation heat should have radiated away into space. The fact that HD 10546b remains so luminous supports the theory that it formed through rapid gravitational collapse rather than gradual accretion. Direct observations reveal that HD 10546b is gravitationally clearing its orbital zone. The planet has carved a gap in the protoplanetary disk 808 million miles wide. Computer simulations indicate that only planets with masses exceeding 5 Jupiter masses can create observable gaps through gravitational interactions. The size of the gap suggests HD 10546b weighs at least 10 to 15 Jupiter masses. Spectroscopic analysis of the system reveals emission lines from sulfur monoxide. This molecule forms only under conditions of extreme temperature and pressure. Its presence indicates shock waves propagating through the disk material. These shock waves result from violent gravitational interactions between the massive planet and a surrounding matter. The planet is literally shocking the disk material through its gravitational influence. The host star HD 10546 contains 2.4 solar masses and burns at a surface temperature of 18,932 degrees Fahrenheit. This makes it a B-type star, one of the hottest and most massive stellar types. Such stars evolve rapidly, maintaining stable hydrogen burning for only 100–200 million years before exhausting their nuclear fuel. The rapid stellar evolution creates a time constraint for planetary formation. HD 10546b must complete its growth within the next few million years before its host star begins evolving off the main sequence. When massive stars exhaust their core hydrogen, they expand into supergiants and eventually explode as supernovae. Any planets in the system face destruction from stellar evolution. This time pressure may explain HD 10546b's rapid formation. The planet had to grow quickly or risk being destroyed by stellar evolution. Traditional core accretion couldn't operate fast enough. Only gravitational instability could create such a massive world within the available time frame. Future observations with the James Webb Space Telescope will determine HD 10546b's mass and composition definitively. Webb's unprecedented infrared sensitivity can penetrate the dusty circumplanetary disk to observe the planet directly. Spectroscopic analysis will reveal atmospheric composition and confirm whether this object truly represents the largest planet ever discovered. If HD 10546b possesses the extreme characteristics suggested by current observations, it will redefine our understanding of planetary limits. The discovery proves that planets can form under conditions far more diverse than previously thought. Young stellar systems can host objects that blur the boundaries between planets, brown dwarfs, and failed binary companions. The existence of HD 10546b demonstrates that the universe doesn't respect our human categories or theoretical limitations. Nature operates according to physical laws, but those laws permit outcomes far more extreme than our Earth-based experience suggested. We've spent centuries developing planetary formation theory based on 8 familiar worlds. Now we discover that our sample was hopelessly inadequate. HD 10546b represents a paradigm shift in planetary science. This world suggests that the most massive planets form through processes completely different from those that created our solar system. Giant planets can condense directly from protoplanetary disks, achieving enormous sizes in cosmic eye blinks. The traditional distinction between planetary and stellar formation may be artificial. Young planetary systems can host objects that challenge every definition we've created. Worlds massive enough to fuse deuterium, yet still behaving like planets. Giants large enough to house hundreds of Jupiters, yet maintaining planetary orbits. Objects that exist in the liminal space between planet and star, defying our attempts at classification. HD 10546b stands as the ultimate example of cosmic impossibility. a world that shouldn't exist according to everything we thought we knew about gravity, matter, and planetary formation. Yet there it orbits, 360 light-years away, slowly accreting material from its circumplanetary disk, growing ever larger in defiance of our theoretical predictions. A reminder that the universe operates according to rules far more permissive than our limited imagination suggested. The discovery of exoplanets has fundamentally shattered our solar system-based intuition about what constitutes normal planetary behavior. For centuries, astronomers built theories around 8 familiar worlds orbiting in predictable patterns. We thought we understood the rules. Rocky planets close to stars, gas giants farther out, orderly spacing, circular orbits. Then we discovered that our cosmic neighborhood represents just one possibility among countless exotic arrangements. Hot Jupiters were considered impossible before 1995. The idea of gas giant planets orbiting closer to their stars than Mercury orbits our Sun violated every model of planetary formation. Gas giants needed cool temperatures to condense from stellar nebulae. They required distant orbits to accumulate the massive atmospheres we observe. Yet hot Jupiters turned out to be one of the most common planetary types in the galaxy. Our impossibility became cosmic routine. Super-Earths. Rocky planets weighing between 1 and 10 Earth masses represent the most abundant planetary type we've discovered. These worlds fill the size gap between Earth and Neptune, a gap that doesn't exist in our solar system. We have no local example of the galaxy's most common planet. It's like studying mammals without ever seeing a rodent. Our sample was not just incomplete, it was fundamentally unrepresentative. Mini Neptunes. Worlds slightly larger than Earth but much smaller than Neptune also dominate galactic planetary populations despite being completely absent from our solar system. These planets typically possess thick hydrogen atmospheres surrounding rocky cores. They exist in a size range where our solar system contains nothing. We're trying to understand cosmic diversity using a sample that lacks the most common planetary types. Retrograde planets, worlds that orbit in the opposite direction to their star's rotation, challenge every model of planetary system formation we've developed. Planets should form from rotating disks of material that naturally orbit in the same direction as the star spins. Yet we've found dozens of worlds traveling backward. These planets must have experienced violent gravitational encounters that flipped their orbits, cosmic billiard ball collisions that flung them into reverse. The discovery of free-floating planets, rogue worlds drifting through interstellar space without any host star, revealed an entire population of cosmic orphans we never suspected existed. Conservative estimates suggest that billions of these planetary wanderers drift through our galaxy, ejected from their birth systems by gravitational interactions with other planets. Some may be super Jupiters more massive than anything in our solar system. Invisible giants traveling the dark void between stars. These rogue planets challenge our definition of what constitutes a planetary system. If planets can exist without stars, orbiting the galactic center like any other stellar object, are they still planets? Do they represent a separate category of cosmic body? Our classification systems assume planets orbit stars, but the universe seems unconcerned with our definitional boundaries. Circumbinary planets orbit 2 stars simultaneously, experiencing the complex gravitational dance of binary stellar systems. Kepler 1647b maintains a stable orbit around 2 Sun-like stars, completing its year in 1/107 Earth days. The gravitational mathematics of such systems defied solution until computer simulations revealed narrow zones of stability. These worlds experience double sunrises and sunsets, alien skies lit by binary stellar companions. Some planetary systems achieve even greater complexity. PH1b orbits a binary star pair that itself orbits another binary system. This world exists in a quadruple stellar system where 4 stars illuminate its sky. The gravitational interactions create orbital dynamics so complex that long-term stability seems impossible. Yet somehow these worlds endure. Polar planets orbit perpendicular to their star's equator rather than in the expected disk plane. HAT P11b travels in an orbit inclined 103 degrees to its star's rotation axis. It's nearly perpendicular to the plane where planets should form. These worlds suggest that planetary systems can be completely reorganized after formation. Gravitational interactions can flip entire planetary orbits into impossible orientations. Extremely eccentric orbits create worlds of seasonal extremes that dwarf anything in our solar system. HD 80606b follows an orbit so elongated that it approaches within 2.8 million miles of its star before swinging out to 84 million miles. During closest approach, the planet receives 825 times more radiation than at its farthest distance. Imagine seasons where the difference between summer and winter involves being closer to or farther from the Sun than Mercury versus Earth. The atmospheric conditions on these extreme worlds defy terrestrial analogies. Planets with vaporized rock atmospheres experience liquid rock rain on their night sides. WASP-76b and similar worlds demonstrate that alien conditions are literally alien to any Earth-based experience. These planets exist in states of matter that have no analog in our everyday world, where the boundaries between solid, liquid, and gas become meaningless under extreme temperatures and pressures. The cotton candy planets we've discovered challenge our understanding of matter itself. Worlds with densities lower than Cork somehow maintain gravitational coherence across volumes larger than Jupiter. These objects suggest heating mechanisms we don't fully understand, or perhaps exotic states of matter that only exist under planetary scale conditions. The physics of extremely low-density objects operating at planetary scales remains largely theoretical. Each new discovery expands our definitions of habitability, composition, and orbital dynamics. Red dwarf stars, the most common stellar type in our galaxy, create tidal locking conditions where planets show the same face to their star permanently. One hemisphere experiences eternal day, while the other endures perpetual night. Yet these worlds might maintain temperate zones at the terminator, the boundary between light and dark. Ocean worlds beneath thick ice shells may harbor subsurface life completely independent of stellar radiation. Europa, Enceladus, and Titan in our outer solar system demonstrate that habitability doesn't require surface liquid water. Tidal heating from gravitational interactions can maintain liquid oceans for billions of years. These worlds expand the habitable zone to include regions we previously considered frozen wastelands. Super-Earths may possess atmospheres so dense they create greenhouse effects powerful enough to maintain liquid water at distances where smaller planets would freeze. Atmospheric retention scales with planetary mass. Larger worlds can hold onto thicker atmospheres for longer periods. This means the traditional habitable zone, the narrow band around stars where liquid water can exist, may be much wider for massive rocky planets. Carbon-rich planetary systems may form diamond planets, worlds composed primarily of crystallized carbon rather than silicate rocks. These exotic compositions result from stellar nucleosynthesis that produces unusual ratios of carbon to oxygen. Diamond planets would possess completely different geological processes, thermal properties, and evolution paths compared to silicate worlds like Earth. Even familiar gas giants may hide rocky cores larger than entire terrestrial planets. Jupiter's core may contain 15 to 25 Earth masses of heavy elements compressed into a region smaller than Earth itself. These planetary hearts remain hidden beneath thousands of miles of metallic hydrogen atmosphere. The boundary between rocky planet and gas giant core becomes arbitrary when cores exceed the mass of terrestrial worlds. The arbitrary nature of our classification system becomes apparent when examining boundary objects. The 13 Jupiter mass limit separating planets from brown dwarfs represents human convenience rather than physical reality. Nature creates a continuous spectrum of objects with masses ranging from rocky planets to massive stars. Our categories impose artificial boundaries on phenomena that exist as smooth gradients. The diversity we've observed represents only the beginning of a much larger scientific journey. Current detection methods favor large planets orbiting close to bright stars. We're sampling the easiest targets rather than representative populations. Future telescopes will reveal smaller worlds, planets in wider orbits, systems around fainter stars. Each technological advance will uncover new categories of impossible worlds. The statistical analysis of known exoplanets suggests we've barely begun cataloging cosmic diversity. If our local sample of a few thousand confirmed planets already includes cotton candy worlds, diamond planets, lava planets, ice giants, super-Earths, mini-Neptunes, hot Jupiters, and rogue planets, what exotic populations await discovery in the trillions of planetary systems we haven't yet studied? Every impossible planet we've discovered forces us to expand our understanding of what's physically possible. The universe operates according to natural laws, but those laws permit outcomes far more diverse and extreme than our Earth-based intuition suggested. We've learned that normalcy is a human concept that doesn't exist in nature. The cosmos creates whatever configurations satisfy the fundamental forces of physics. Our current understanding represents merely the opening chapter of planetary science. We've confirmed that planets exist in configurations we thought impossible, around stellar types we considered unsuitable, in orbital arrangements we deemed unstable, with compositions we believed incompatible with planetary formation. Each discovery reveals that our theoretical limitations were more restrictive than nature's actual boundaries. In a universe containing planets hundreds of times Jupiter's volume, Earth appears extraordinarily small. If HD 10546b were scaled down to the size of a basketball, our entire world would be smaller than a grain of sand. You could hold the basketball in your hands and never notice our planet, even with a magnifying glass. We exist on a cosmic speck orbiting an ordinary star in an unremarkable galaxy. Yet somehow, impossibly, this tiny world became the stage for the most complex phenomenon we know: life itself. The cosmic giants we've discovered are predominantly gaseous, inflated atmospheres of hydrogen and helium surrounding cores of exotic matter. These worlds cannot support life as we understand it. No solid surfaces exist beneath their crushing atmospheres. No stable chemistry can operate at temperatures exceeding thousands of degrees. The cotton candy planets, with their impossibly low densities, would offer no foundation for biological complexity. They represent cosmic spectacles rather than potential homes. Earth's biological complexity developed under exceptionally stable conditions on a rocky planet with moderate temperatures. Liquid water persisted on our surface for nearly 4 billion years. Atmospheric composition remained within narrow bounds compatible with carbon-based chemistry. Geological processes recycled essential elements without creating runaway greenhouse or glaciation effects. These conditions appear increasingly remarkable as we discover the chaos that characterizes most planetary systems. Planetary systems containing super-Jupiters often exhibit chaotic architectures that would destabilize Earth-like worlds. Massive planets migrate inward from their birth locations, disrupting the orbits of smaller rocky planets. ejecting them from habitable zones or flinging them into stellar furnaces. The gravitational violence that creates hot Jupiters typically destroys the stable circular orbits necessary for long-term biological evolution. Jupiter's presence in our solar system has protected Earth from catastrophic comet impacts for billions of years. The giant planet acts as a cosmic vacuum cleaner, capturing or deflecting dangerous objects before they can reach the inner solar system. Computer simulations suggest that without Jupiter's gravitational shield, Earth would experience major impacts every few million years rather than every 100 million years. Such frequent bombardments would prevent the emergence of complex life. Paradoxically, the extreme giants we've discovered might make their systems less suitable for developing complex life. Planets like HD 10546b, with masses exceeding 20 Jupiters, would gravitationally dominate their entire systems. Any rocky planets in such systems would experience constant orbital perturbations, preventing the stable conditions necessary for biological evolution. The universe's most impressive planets may be the least hospitable to life. The habitable zone around stars represents the narrow region where liquid water can exist on planetary surfaces. For Sun-like stars, this zone extends from approximately 78 million to 180 million miles. Earth orbits comfortably within this range at 93 million miles. But the habitable zone varies dramatically with stellar type, and most stars in our galaxy create conditions hostile to Earth-like life. Red dwarf stars constitute 75% of all galactic stars, but planets in their habitable zones face unique challenges. The habitable zone around red dwarfs lies so close to the star that planets become tidally locked, showing the same face to their star permanently. One hemisphere experiences eternal day, while the other endures perpetual night. Extreme temperature gradients drive atmospheric circulation patterns that may strip away planetary atmospheres entirely. G-type stars like our Sun represent only 7% of galactic stellar populations. These stars burn at moderate temperatures for billions of years, providing stable energy sources for biological evolution. Most other stellar types either burn too hot and die too quickly, or burn too cool and produce destructive stellar flares. The specific stellar conditions that permit long-term biological evolution appear relatively rare. Earth-sized rocky planets seem statistically uncommon compared to super-Earths and mini-Neptunes. Most planetary systems contain worlds, 5 to 4 times Earth's radius. These planets typically possess thick atmospheres that create surface conditions incompatible with terrestrial life. Earth's specific size may be crucial for maintaining the thin atmosphere and moderate greenhouse effect that permit liquid water. Our planet's chemical composition, including the precise ratios of heavy elements, may be cosmically unusual. Earth formed in a region of the galaxy with specific metallicity, the abundance of elements heavier than hydrogen and helium. This metallicity affects planetary composition, atmospheric retention, and geological processes. Most regions of the galaxy have different metallicity levels that would produce planets with different chemical properties. Earth's magnetic field protects our atmosphere from erosion by solar wind. This magnetic shield results from our planet's molten iron core and specific rotation rate. Planets without strong magnetic fields gradually lose their atmospheres to space. Mars likely possessed a thicker atmosphere early in its history, but lost most of it when its magnetic field weakened. Maintaining atmospheric protection requires specific internal conditions that may be uncommon. The Moon stabilizes Earth's axial tilt, preventing chaotic variations in climate over geological timescales. Without lunar stabilization, Earth's axis would wobble dramatically. causing extreme seasonal variations that would stress biological systems. The moon formed through a giant impact that was statistically improbable. Most planets either lack large moons or possess multiple smaller satellites that don't provide comparable stabilization. Planets with multiple large moons experience complex tidal forces that could destabilize climate patterns. While our single large moon creates predictable tides that may have aided the transition of life from ocean to land, multiple large moons would create chaotic tidal patterns, rapidly changing sea levels, and unpredictable environmental stresses. Earth's plate tectonics recycle carbon between atmosphere, oceans, and solid rock, maintaining atmospheric composition within bounds compatible with life. The carbon cycle regulates global temperature through geological feedback mechanisms. Planets without active plate tectonics may experience runaway greenhouse effects or permanent glaciation as carbon becomes trapped in surface reservoirs. Terrestrial biodiversity developed over 3.8 billion years of relatively stable evolution. Despite periodic mass extinctions that eliminated 99% of all species that ever existed, life persistently recovered and diversified. This resilience suggests either exceptional biological robustness or remarkable statistical luck. Both factors may be necessary for complex ecosystems to develop. The emergence of technological civilization represents an even more improbable development. Intelligence capable of understanding cosmic scales evolved only once on Earth, despite billions of years of biological experimentation. The Drake equation estimates between 1 and 100,000 communicating civilizations in our galaxy currently. This enormous uncertainty reflects our ignorance about the probability of technological development. The Fermi paradox questions why we haven't detected signals from advanced civilizations despite the vast number of potential habitable worlds. Perhaps technological civilizations are extraordinarily rare. Perhaps they typically destroy themselves before achieving interstellar communication. Perhaps they develop technologies we haven't imagined. Or perhaps we simply haven't looked long enough or in the right places. Planets around young stars haven't had sufficient time for complex evolution. Stars younger than 1 billion years haven't provided stable conditions long enough for technological civilizations to develop. Planets around ancient stars may have lost their atmospheres or experienced stellar catastrophes as their host stars evolved. There may be a narrow temporal window during stellar evolution when complex life can flourish. Our existence in a universe containing planets that challenge the very foundations of physics reveals a profound cosmic irony. We are simultaneously insignificant on cosmic scales, yet unique in our ability to comprehend that insignificance. The vast majority of matter in the universe exists in states incompatible with complexity, yet somehow, under specific conditions that appear exceptionally rare, matter organized itself into configurations capable of consciousness. The impossible planets we've discovered, worlds that float like cosmic soap bubbles, giants that approach stellar masses, hellscapes where iron rains from vaporized skies, expand our perspective on what the universe permits. Yet none of these exotic worlds could have produced the phenomenon reading these words: complexity, consciousness, the ability to contemplate cosmic scales. These properties emerged only under the precise conditions that exist here. Think about the statistical improbability of your existence. You are composed of atoms forged in stellar cores billions of years ago, arranged into patterns of extraordinary complexity on a planet whose formation required countless unlikely events. Orbiting a star of precisely the right type, in a galaxy containing trillions of worlds, most of which are hostile to any form of organization more complex than plasma. Yet here you are, a temporary arrangement of cosmic matter that has become aware of itself, capable of understanding distances measured in trillions of miles, comprehending timescales spanning billions of years, contemplating the existence of worlds that dwarf your entire planet. You represent the universe becoming conscious of itself, matter achieving the impossible feat of self-awareness. The cotton candy planets with their impossibly low densities, the giants so massive they approach stellar ignition, the hell worlds where metals rain from superheated skies. All these cosmic extremes serve as backdrop to the most remarkable phenomenon we know, the emergence of consciousness capable of discovering and understanding these very extremes. In contemplating these impossible worlds, you participate in the most extraordinary development in cosmic history, the evolution of matter capable of comprehending its own context. Understanding that you exist on a small rocky planet orbiting an ordinary star in a universe containing worlds that challenge the very laws of physics. This understanding itself represents the most impossible thing of all: consciousness arising from cosmic dust to contemplate the infinite. If you're still awake, it's because the content was really good. So take a moment, leave a like, and subscribe to the channel. It helps a lot. And if you want to keep watching, just click on the video that's appearing right now. I'll see you there.